All right. Good afternoon, everybody, and welcome to the Petro-Teach webinar on classic measurements versus image processing in Porous media. My name is Hassan Karimai, represent Petro-Teach today and act as facilitator in today's webinar. As you already heard from the organizer, you are entering as a listening only mode and muted. Before we proceed to the event, let us check if you receive my voice properly. There is a window in front of your platform, and by clicking on the arrow, you will see the full window version with a chat box. Please type the word hi or hello or something to make sure that we have established the full communication. Okay. Yes. Seems everything is okay. So the agenda of the event today begins with a brief introduction to Petro-Teach, and then we will introduce our distinguished instructor, Professor Reza Azin. Next, we follow and listen to the webinar lecture, which lasts 30 to 45 minutes, or maybe even more. And finally, we will have Q&A session for approximately 15 minutes. So Petro-Teach is a global provider of high-quality training solutions to the oil and gas industry. We are providing almost 150 training courses by up to 50 distinguished instructors with high track record from both academia and industry. Our training styles include online, public, and in-house courses. Due to the COVID-19 pandemic, Petro-Teach is mainly focused on the distance learning. And for more information, please visit our website, www.petro-teach.com, and download the course catalog. You may also follow us in social media, and do not forget to subscribe and watch our videos on the Petro-Teach YouTube channel. The webinar today is part of the 20 webinar series that Petro-Teach is offering during this year. We started by Nightmare of High-Depth Blockage by Professor Bahman Tauhidi in September and ended up with Petroleum Economy with Professor Wumi Idedar on Monday 21st. And in the meanwhile, we had several webinars, including different disciplines from petrophysics and also seismic and hydraulic fracturing and 3D printing in geology. And in October, also, we started with casing and cementing by Jerry Rusnak. And today, Professor Azin will talk about classic measurements versus image processing in porous media. Also, we will have advanced analysis of carbonate system by Professor Maria Muti, and finally SAGD and solvent SAGD design and analysis by Dr. Mazda Irani in October. And also in November, we will have almost 6 webinars, and December 4 seminars we will have. So we welcome and are pleased that Professor Azin can join us today. He has over 15 years of experience. And as you can see, he has PhD in petroleum engineering in 2007. He has more than 20 years of experience in academic research, training, and industrial consulting in chemical process and petroleum reservoir. He is senior lecturer and researcher in reservoir and chemical process engineering. His main focus is on experimental as well as theoretical and numerical solutions to the oil and gas industry, seeking solutions to reservoir and process engineering problems using advanced and high-tech approach. His areas of interest cover oil and gas reservoir, underground gas storage, PVT analysis and modeling, surface facility design, carbon management, and process simulation. He was supervisor for more than 50 master students and also PhD theses. He has published plus 80 journal papers and more than 50 conference papers he has presented so far. He is also author of some books, Vapor Extraction or VAPEX process in heavy oil fracture system, and also simulation study of underground gas storage. So today we are pleased that Professor Azin can join us today. So let's move to the presentation, and I wanted to remind you all that you can post your questions using the same chat box introduced at the beginning. At the Q&A session after the lecture, they will be answered. So I'm going to hand over the talk to Reza to address his presentation. Yes. Here you are, Reza.
Okay. Do you hear me?
Yes, we can hear you.
Hello and good evening to everybody. First of all, thank you, Mr. Karimai, for giving me this opportunity to present a part of our works in Persian Gulf University. Today, I'm going to present a number of experimental findings and theoretical findings of our works on flowing Porous media. The main contents of this presentation will cover the pre-Darcy flow versus Darcy flow, and then I will proceed with porosity versus permeability. I will share some of the image processing experiences with, I will show you some classic measurements, and then I will go to the relative permeability concept, and after that I will present some of the preliminary results of the phase trapping studies here in Persian Gulf University. All of these topics, I think, are quite familiar by the reservoir engineers, and I am trying to approach these concepts through a novel models. The Darcy equation is the basic flow equation in porous media. All of us are familiar with this equation. This is an empirical equation which was developed by Darcy in 1856, and the correlation is based on the experiments on loose unconsolidated sandpaper, and he used water as the flowing fluid under steady-state flow conditions and laminar flow. These are the familiar rules and conditions where the Darcy equation applies, but after him, researchers extended the model to other conditions, I mean other flowing conditions and other fluids and other geometries. After Darcy, researchers observed that there are some other flowing conditions like Brinkman flow, as you can see here. In this slide, you can see the equations, which is a little bit different from the Darcy equation. And the other flowing conditions is the viscous flow or Navier-Stokes flow equation. It's quite different from Darcy, but researchers have already shown that the Darcy equation can be extracted and can be derived from the Navier-Stokes equation as well. But one of the questions ahead of the reservoir engineers is that is the Darcy equation always valid in the reservoir or not? And this is a topic of research already undergoing in Persian Gulf University, and you can see here the answer to this question is a little bit different from experimental and requires some modeling approaches. And you can see here a schematic of the flow in porous media here, and there are some differences between flow in porous media and the bulk of fluid, and the wall of the pore throat and the thickness of the pore throat are dominating important factors in determining the flow regime. And we need to understand these differences from Darcy to Brinkman or even to the viscous flow. And you can see here some of the preliminary results. When you have Darcy velocity profile, the velocity is quite the same throughout the pore throat. But if you have Brinkman or Navier-Stokes or viscous flow, the profile of velocity is a little bit more circular or hyperbolic rather than a constant. And we can understand and we can determine the differences between three flowing regimes, and we can determine the conditions which flowing regime is predominating in porous media. So another approach for determining the petrophysical properties is the image processing. You are all familiar already with the classic measurements, I mean nitrogen or helium gas volumetric methods for determining porosity and permeability. The novel image processing covers CT scanning or CBCT, I mean dental CT scanning or micro CT scanning. As you can see here in this figures, some of the devices which are recently, I mean during the past 15 years, used to apply the image processing technique for determining the porosity and then determining the permeability. These equipment are already available in the area, and we rent them sometimes to take pictures and images. As you can see in the right corner here, some of the samples I'm showing you, and in this slide you can see the processes of interpretation of the images. After taking images, we need to do image segmentation and then reconstruct the model and process the images and obtain a new observation of the model here. You can see in the this slide. And after that, we can use numerical techniques to determine the porosity of each slice, and then model the porosity data, combine the porosity data to obtain an average value for the core. So in this slide, you can see the results of one of our publications in Journal of African Sciences. Some of the models you can see here, there is a good match between image processing results and classic porosity measurement, but sometimes there is a large difference between the results, and we have observed that the resolution is always a challenge in this approach. Based on the observations, you can see that there is a good porosity estimate by CT scanning for sandstone and some calcite carbonates, but it is not so good for heterogeneous dolomite samples, marl, and evaporates samples. And we need higher resolution to overcome the phenomena like cementation and weathering that may interfere with the image processing. So in this part, we have tested the dental CT and clinical CT scanning, but we found that for some dense materials like carbonates, I mean dolomites and evaporates, we will need the micro CT scanning. The other concept of flowing conditions in the porous media is that the pre-Darcy flow. The pre-Darcy flow means that conditions that are not the same as the Darcy zone, as you can see in this slide. The reservoir engineers have already distinguished the Darcy zone and the post-Darcy zone, which is similar to the transition and sometimes turbulency conditions. But the concept of pre-Darcy zone has not been very good understood in the reservoir engineering. Mainly, I think the other disciplines like soil engineering and environmental pollution have distinguished the pre-Darcy zone with Darcy zone. And the reservoir engineers have already basic information and are familiar with the concepts like Horsheimer flowing condition and inertial effects and slip flow, which are all related to the post-Darcy conditions. But there are some questions regarding the validity of the Darcy equation at very low velocities. For example, we need to know the onset of Darcy flow, the conditions where the pre-Darcy flow predominates, and the effect of fluid and rock properties, which determine the flowing conditions and distinguishes between pre-Darcy flow and Darcy flow. It is important to understand the pre-Darcy flow in porous media and in reservoir flowing conditions, because the pre-Darcy equation is shown that to have a different equation, and a different flowing equation will affect the simulation process. As you can see here, there are 12 different models proposed for pre-Darcy flow, and we need to understand which of them is valid for our experiments and for our reservoir. In order to understand the conditions of pre-Darcy flow, we have conducted a number of experiments in sandpack flooding setup and a number of experiments in core flooding using dense samples. And we used the water, liquid condensate, hydrocarbon gas condensate, normal hexane and normal hexane as liquid, and nitrogen, methane, and carbon dioxide as the gases. Here you can see some of the results. The slides compare the effect of permeability for different liquids, and you can clearly observe that not all of the data pass to the origin, which is the basic assumption by the Darcy equation. And this is the case for condensate, for normal hexane and normal hexane at all permeabilities. And we can distinguish the pre-Darcy zone with non-Darcy and Darcy zone. In this slide, we have tested different Reynolds numbers in porous media, and we have plotted the friction factor versus Reynolds number. You can see the onset of pre-Darcy at very low Reynolds numbers, and here in the right one, you can see the onset of pre-Darcy flow at very low Reynolds, and the onset of non-Darcy flow at higher Reynolds numbers. And we have observed that the different Reynolds numbers, number equations confirm with each other. This is the summary of the data, which determines the pre-Darcy and Darcy and non-Darcy equations for all liquid types and for all particles and for all permeabilities we have studied. And you can see here that if even for the gas flow, we can observe the pre-Darcy flow. It is interesting to see that most reservoir engineers believe that the gas flow is mainly Darcy in the reservoir, and approaches the non-Darcy, I mean the transition flowing conditions near the wellbore. But we have observed in the laboratory that even for the gas flow, we can expect the pre-Darcy flowing conditions. And you can see here the results for nitrogen and methane and carbon dioxide. And this curve shows the ratio of the mobility for Darcy equation and for pre-Darcy equation. You can see here, as the superficial velocity increases, the flowing conditions approaches the Darcy flow. And the case of the pre-Darcy flow in dense cores were also studied using carbonates, calcite, chalk, and dolomites. All samples were taken from Zagros Mountain in different formations. You can see here the Asmari formation, the Avajari, Dalan, and Gatsaran and Kangan formations. And the normal permeabilities are relatively low. And here you can see the results of the pre-Darcy flow in dense cores. And here the analysis of the dimensionless Reynolds number, and then you can distinguish between the pre-Darcy, Darcy, and non-Darcy flowing conditions for dense samples. So we can conclude that the pre-Darcy flow may be observed both in the loose and unconsolidated and the consolidated and dense sand core samples. The other concept, which is already familiar to all of the reservoir engineers, is the relative permeability concept. You understand this equation. The relative permeability is the ratio between effective and absolute permeability, and we know that this term is very critical for reservoir simulation and reservoir modeling. And basically, the relative permeability is a function of saturation. If we take a look at the available correlation for estimating the two-phase relative permeability, we can see that there are a number of models for oil and water systems, or gas and water, or oil and gas systems. And some of the equations and correlations are proposed for sandstone only, but some of them are proposed for both sandstone and carbonates. So we have this categorized the available correlations, and then we have tested them. Some of the correlations have adjustable parameters, and some of them have no adjustable parameters and are fixed. And we have at the first attempt to approach the validity of the models for the carbonate systems and for our systems of study, we tested them and realized that not all of them are applicable for all systems. You can see here in this slide that the bar chart shows that some of the models show high average root mean square error, but some of them are a little bit better, working better than others. And this decision tree is proposed at the first attempt to select a good model based on the rock type, based on the wettability conditions, and based on the fluid phase. You can see some times the LET model works better than others, and sometimes Tegmont and McCaffery model works better. And in this model, in this slide, you can see the comparison between different relative permeability correlations for sample data. So there is a it is obvious from this slide that not all correlations fit our experimental data. And this is a challenge for all of us when we are working with the data taken from a laboratory for a specific field. In order to overcome this challenge, the first solution will be optimizing the existing correlations. And the second solution will be proposing a new set of correlations which cover a wider range of data with a better accuracy. And we have attempted both. In the first approach, we try to optimize the available correlations for a large number of data. And then at the next step, we propose a set of correlations based on the available data and based on our measurements. I will show you some of them. The new correlation was proposed using a machine learning approach, and we proposed a new correlation based on saturation, molecular weight, API gravity of the oil, and the ratio between permeability and the porosity. For the gas phase, you can see the same approach, and we use the S star in normalized saturation, as you can see by the equation. And the new correlation is shown in this slide. You can see here the relative permeability for gas and the relative permeability for the oil phase. And here in this slide, you can see the optimum R square and root mean square error of test and train process for this data based on the results. The best optimized models, available models, are compared with the new empirical correlation. For example, here the Korean model shows R square of equal to 0.68 after optimization, but the new empirical correlation shows around 0.97. And for the oil phase, you can see a better approach and a better estimate by the new empirical correlation. And you can see here point-to-point analysis of the experimental data and prediction results for each phase, for gas phase at the top and for the oil phase at the bottom. Here you can see. In the next step, we started preparing and gathering new data using the SAMPAC experimental setup in the laboratory in Petro-Teach University. And here you can see the design of experiment approach and then development based on the development of the model and testing of the model based on the genetic programming. And the schematic of the setup is shown here. Here I can show you some of the new experimental data taken in our laboratory, and these data were used to validate and check the validity of the proposed correlation. Here, the new correlation are shown here in this slide for the gas phase and for the oil phase. And the match between the new correlation and the experimental data is shown in this slide. Again, we can see a good match between the proposed model and the experimental data is obtained. The last item I'm going to present you is the phase trapping. The phase trapping concept is a little bit familiar, but by the reservoir engineers, we know that the target of enhanced oil recovery approach is to mobilize the trapped phase in the oil reservoirs, and the target of the enhanced gas condensate recovery approach is to remobilize the trapped gas condensate in the gas reservoirs And on the other side, the target of the carbon capture and sequestration approach is to trap this carbon dioxide inside the reservoir. You see, the concept of the trapping is different from CCS and from EOR and EGR. In the CCS, the trapping process is a favorable process. However, in the EGR operations, the trapping is unfavorable, and the reservoir engineer and the operator should overcome the trapping. We have already working on the trapping, and we can see here some of the concept of a schematic of the phase trapping in oil reservoir. After water flooding, we have some of the oil is left behind in the reservoir, oil droplets trapped in the pores, and in the gas condensate reservoirs, when the reservoir pressure declines during the production, a bank of condensate forms and propagates to near the wellbore, and we can see the condensate production. We can analyze the condensate drop out here by analyzing the production data and checking the CGR data with time. And this is another aspect of the unfavorable trapping in gas reservoirs. You can see here. And in this slide, I can show you the parameters affecting the capillary phase trapping. You can see here the porous structure, the rock and fluid interfacial properties, the permeability, capillary pressure, and fluid properties, relative permeability, initial saturation, and pressure gradient, pressure decline in the reservoir are important parameters affecting the trapping in the source media. In order to better understand the experimental better understand the trapping mechanism, we have designed some of the experiments in sandbags at the first stage. Here you can see the initial and residual, IR curves, IR plots taken in the right hand. You can see the data taken from literature, and the blue and purple points are the experiments they have already done in our laboratory. And in the IR curve on the left side, you can see the experiments with kerosene, normal hexane, normal ethane, and condensate as liquid, and CO2 as a gas phase. The effect of IFT is shown below, and the effect of fluoride as well in below. These are the new data generated in the experiments in the laboratory and published in the journal paper recently. So I can show you the effect of capillary number, the match with optimum correlations. There are a number of correlations available for predicting the phase trapping. We have checked them, and we have tested them for our experiments. And here in the lower plot, you can see the effect of mobility using the normal hexane and normal heptane experiments. As a conclusion, we have found that image processing a useful tool for rock property estimation for the first part of the experiments. Also, a wide range of flowing conditions and flow regimes were described and distinguished from pre-Darcy to post-Darcy in another set of experiments for both sandpack and the dense core samples. In the relative permeability experiments, we proposed novel correlations and new experiments. And in the phase trapping, which is the newest research activity in our laboratory, We have started with some preliminary experiments and optimized already the available correlations, and we are going to continue this approach during the next couple of years. These are the published papers from our works from about 30 years ago to today. And then this is the end of my presentation. Thank you very much for being here as the audit, and I hope I've provided you with some useful data and information, and I will be glad to answer your questions. Thank you very much.